All right. Good morning. Just want to make sure my microphone isn't.
We can hear you.
Okay. Yeah, no, it's not, sometimes it crackles a bit. All right. So thanks for coming. You should thank your future self for coming. Because knowing the skills we'll go over today, you'll be using in 110 and your life. So I'm just going to show you, right, here are the two assignments. You can access them through Canvas, but this is the practice which I suggest you do first. All right. And we have an RMS question, some OPAMP questions, RC questions, RLC questions, and then a filter question. All right. And I thought, now, just so you know, I'm in the process of adding like 10-minute videos to these questions, so that if you're lost, stuck, or whatever, you can just click on it and it's right there. It can be super hard to find information. So let's do an RMS problem, or root mean square. All right. And we use it to convert a so we convert a periodic signal, right, into a number so that we can compare it to DC. So if I have a 1 volt DC signal, right, how much power in relation, if I have excuse my drawing, but I have a sine wave. How do I compare those, right? Of course, probably this one might be memorized. If you take VP and divide it by the square root of 2, right, that number then can be used to compare powers, right? So if power DC is just V times I, well, what about power of that AC? Well, that would just be V RMS times I RMS. And of course, you don't usually do it that way. You have some kind of load where it's the current times the resistance, or the voltage divided by a resistance. And even though we don't use RMS so much in this class, it's this stepping stone to something called the Fourier series which I can take any arbitrary signal and convert it into cosines and sines and add them all up. And I can kind of analyze that signal like that. All right. So actually, and just checking, right? You are still seeing the screen, right? Because normally there's like a
we can
box.
still see the screen. We can see LT Spice now.
Okay, great. So here's a signal, right? And we're going to calculate the RMS of it as an example. And you can see it's a trapezoid. One has a slope higher than the other. It's on for a certain amount of time. And while we're going to do the RMS of it right now, when I said I can break this up into sines and cosines, or all cosines and with a phase, I'll just show it to you. There's something called the fast Fourier transform. Okay. And okay. So each one of these peaks is a sine wave or cosine with a phase. So if I just left click on that and put the marker right on one of those peaks, right? It's I have a magnitude and then a phase. So these are all cosine waves with a delay. This one's 150 degrees. And you can see all of these. Okay, now this is a numerical thing, and it can, it will have, if you will, artifacts, right? And so it's actually drawing a line between these, but it only exists really at the dots, right? So it's here, it would be 0. And then not only that, but if you really want to see it, you use a decibel, so you can see that these are an infinite, somewhat infinite series. Okay, so that's what we're going to do in 110 later. But the thing is how can that be useful? Just to give you the idea, I'm going to go back to the linear scale. Is now I know what frequencies are involved, and then I can use filters to amplify a certain frequency, get rid of a certain frequency, manipulate it, things like that. And in fact, the mathematical operation is somewhat similar. Now, if I control left click here on top of the VX, I should get RMS of 1.631. So I'm just going to write that down.
Professor, sorry, can you show one more time how you get the RMS there in the LT Spice?
You mean how I do it in LT Spice?
Yes.
So I'm taking my mouse button, hovering over the symbol in the title here, or in the tool title, the title bar, VX. And then what you can't see is me pressing Control. Oh, sorry. I press Control and then left click. Now, actually, I have a video on that too. And then it pops up. Now, some caveats here is that if you, if you don't do the full period, you get like different answers. So see, this is now 1.7, or if I zoom in, actually here, where it's flat, I get 2 volts, right? So if you don't, so this simulation, it repeats every 6 seconds. I mean, this waveform, The period is every 6, right? So if I don't simulate in, positive integers of the period, I will get the wrong answer. All right. But anyway, and so now I just have to, because it's the example, I want to make sure. So I don't want to write down the wrong problem. So rise, fall, 2, 3. Should be able to remember that. Okay. So 0 second, 1, 2, 6, and it goes up to 2 volts, and it goes up to 2 volts in 1 second. Then it's on for 1, 2 seconds, and then it takes 3 to go down, and this repeats. And that's the other thing that it has in common with the Fourier expansion is that we're saying that this repeats forever, right? And so when we're doing phasors, so, we have the Fourier, but you might recall phasors, and even our impedance discussion from the last time is that those are sine waves that will always exist, right? Of course, they don't always exist, but we can approximate that. All right. So the thing is we're trying to see how much energy is in this, right? And let's just talk about why RMS, right? Is that if I drew this perfectly and took the average, right, I'd get 0. But you know that if you stick your finger in a light socket, which has, 60 hertz sine wave, right? You could say, well, the average peak is 0. Yeah, but the average power is certainly not 0, and you're going to hurt yourself very much. So in order to get a true average or a comparison, right, we have to square this, right? And then integrate over it and then average it, okay? And just as a quick aside, is that if we integrate something, right, this is practically averaging. It's almost averaging, right? And integration is really a precursor to averaging. And in fact, regular integration is averaging, but you just don't scale the output. But when I go and divide it by the period, right, now all I'm doing is finding the average, right? And if you've had some statistics, right, when you're trying to find the error, right, you square the distance from the mean or from wherever it should be, right, and then sum them up and then divide them by the however many samples they were, and then take the square root to get the units back, right? That's really the same thing, except it's done digitally, like it's individual units, where this is continuous, right? So again, this would be 0 for a sine wave or a cosine wave. Yet certainly there's power in sines and cosine waves, as people find out to their detriment. So what do we do to make it better? We square it, right? Now, if this was volts, which in LT Spice it is, now I have this thing in units of volts squared. remember, I want to compare it to a DC signal, right? Well, DC signals come in volts, not volts squared. How do we get back?
Square root it.
Yeah. Yeah. Hey, feel, feel free, right? Feel free to shout it out. So yeah, there's our RMS equation, right? And again, there's some things that we do in the Fourier expansion is we actually find a DC component, this here, right? A kind of a bad RMS or a weaker RMS, right? But you're really just, this is an average, right? And this is just an average of the thing squared. And then again, going forward, you will be doing this quite a bit, just xt, and I'm going to multiply this by a cosine 2, right, dt. But here's the thing, we're not coming up with functions of time, we're coming up with just numbers. And so this is where it's all heading. I'm going to look at the chats.
It's just 2 short comments.
Yeah, go for it.
No, I'm saying that's the summary of the chats. It's not questions. For example, root mean square is literally the root, which is in blue, the mean, which is in yellow, of the square, which is in green.
Oh, okay. So you were just
ways to remember the actual equation and stuff like that.
But I mean, okay. But I just made those colors up on the fly. That I was like, oh, here's a memetic or something that I maybe forgot. You were just coming. Okay.
Yeah.
Oh, it is almost like a fun way to go around. No, it is a fun way. It's not almost like, it is fun. Okay. So I see a question from Kylie. Are average and RMS the same thing? No, but they can be, right? Because, and let's just, it's a great question. So what I'm going to do is I'm going to go on for 1. I'm going to go up very fast. I'm going to go down very fast. And I'm going to stay on for 3. So this should be a 50% duty cycle. Okay. So now, right, you can see that it's either on or it's off. And here it's 1, right? So the time function in this point is 1. So then we would square it, take the, find the area, take the average, and then take the square root. So, nope, they're not the same. Sometimes I forget myself. In this case, it's on half the time. And maybe this should be the first example we do, right? Because intuitively, you would think that this should work, but you're integrating something squared, even though this, but when you take the square root of that average, right? I think that's what's going on. So why don't we, why don't we do that one first? actually. The math should be easy. Oh, did I keep it at 2 volt? No, I kept it at 1. So let's just make everything easy. So xt is going to equal 1 volt when t is between 0 and 3, and it's 0 volts when t is greater than or equal to that. Now we actually have other ways of describing that, but really, so we have 2 domains. Okay. 0, 3, 6, and 1. All right. So let's just write out our equation. 1 over t, 0 to t. And sometimes it's easier to keep things in variable form first. Okay. So right here, it's 0 here. So we can rearrange, we can change this and make our lives a little bit easier and go 0 to t divided by 2 x squared, right? And I'll just write this out. And you can tell that, you know, that that's 0, right? Okay, now I'm just gonna scroll a smidgen down and change colors. So now we know that in this region, right, it's 1. So we can just substitute that. Actually, I usually uh, 1 squared integration with t is t, right? And I'm sorry, I'm gonna have to painted myself into a corner, right? So we have t divided by 2 minus 0. We have the 1 squared. We have the 1 over t, right? The t's cancel. And we get the square root of okay. Somebody just emailed me that the link wasn't working, but I want to see if he's here.
I'm here right now, Professor. That was me.
All right, thanks for the heads up.
Yeah, no problem.
All right, so
$0.707.
hey, yeah, I like that answer because it matches LT spice, right? And so where's that coming, you know? So even though the average, right, of this All right, what's the average, or before we take the square root, right, it's going to be 1/2 voltage squared, right? The average of this is just 1/2 volts. So in the conversion back, right, we're getting actually more power in that signal than one would expect. Okay. So it's, now I'm sure I could find some example, right, that I could get them to be equal, but no. And it's not, you know, you're squaring it and taking the square root, so it's non-linear. So it's not, you know, averaging is linear. Okay. But did that work for everybody? Okay. All right, good. So the next part, and it is a skill that we use all the time in 110, is how to make something complicated simple, all right? So that you don't have to fiddle faddle too much. So let's go back to our, it might not be exactly to scale, but that's 1, 2, 3. Yeah, so it's not to scale. All right, and that's 2 volts, right? So now I want to take RMS of this, right? And yeah, the first thing we have to do is find out what the period is, right? Which in this case is 6 seconds. But still, I tend to leave it there in variable form as long as I can. All right, but now in this case, we've got 3 options. Region 1, 2, and 3. Okay, so now we have 1/t. Let's see, we'll call this region 1. 0. Now, yeah, I could probably say, well, this to t divided by 6, but I'm actually going to put the limit, you know, here, right? And I'm going to call this just x1 t squared dt plus 1 to 3 x2 squared dt plus 3 to 6
Put 3 again.
Did I? Well, then
Should
that
be
was
6,
easy.
Professor,
Yeah, that wouldn't work
on the top.
Thank you. So now the thing is this one, and I'm just going to write the equation right below it. I'm just going to say there's a slope. We'll call it m1t, right? And it's squared. Here, it's actually easy. It's 2 squared. I'll even put the dt's here, right? And here, right, it's really m2t plus b squared dt. But this is a pain. Okay, that's being in pain. Okay, make it easy. All right, and I'm going to come back to that in a second, how to make it easy. But what you also, before you embark on it, is you kind of want to plot out what you're integrating, right? So right.
Professor Parent,
Yes.
weren't the rise, fall, and on times 1, 2, and 3? In this case, it looks like you've written 1, 3, and 2, because the rise time is correct, but then the on time is 2 seconds in these calculations, and the fall time is 3 seconds. Wasn't it the other way around in LT Spice?
The rise time was 1, the on time was 2, and the fall time was 3, right?
I thought the rise time was 1, the fall time was 2, and the on time was 3, because in Spice it's the other.
Let's see.
Yeah.
Let's see. Rise. Oh, yeah. Oh, that would make a big difference. Thank you. Well, I would have found that out to my detriment. So 1, it was on for 3, so that's got to be 4. This comes 4, and the fall time was 2. Yeah. Okay. Thanks. Okay. Now, so let's go back and put a 4 there. So this line here is squared, right? It's going to go up to 4, and it's going to look like that, right? And then it's just going to be flat. And then this is going to be squared. Okay. And now think about it. Even though I can expand this, it's rather a large polynomial to have to deal with, right? Because even with this, right, it's turning into a lot of work, even though each step isn't that hard, right? But here, notice, because it starts at 0, I can just do the slope, whatever that slope is, times t squared, right? Here, I really got to fiddle with it. So what I'm going to do, right, is I still have to integrate for 2 seconds, right? But what if I called that 0 and called that 2 and just reverse the axis, right? Then I can just do m. Then I can just do that, okay? Yeah. Okay. And sometimes, right, if this rise time was the same here, these two areas would be the same, and you could just integrate it once. All right. So a similar problem like this is worked out in the video. All right. This is understanding and breaking it up right? And changing this into something easier. That's really kind of the important part for today, because, and so I think, like I said, given the fact that you have seen RMS, right? And it's this problem or another problem, and that there's a video. I think you can kind of work that out on your own, right? I want to kind of hit the things that maybe you might not have seen, or making it easier. Okay. So I kind of want to go over this problem next, because I do have to leave at 10. And although I am thinking of maybe a Saturday session, not this weekend, but maybe next weekend extra, which would be actually face-to-face in the engineering building. Okay. Can you show the RMS value? Oh, just want to check the value? All right. So maybe some of you, yeah, you're a lot faster than I am. .6317. Do you want better? File. Okay, so I just put the link to that file in the chat. Okay, and you should just be able to direct download it to your own computer, and you'll be learning how to use LT Spice in lab. However, there's nothing like getting ahead of the game. This is the manual, okay? Which tells you how to download LT Spice and things like that. All right. So, I just want to talk a little bit about OPAMPS. And the op stands for mathematical operations. And you can do integration, derivation, taking the derivative. You can do summing, positive and negative. You can take log functions. You can raise things to the power of E. Now, yeah, if you have integration, you have averaging, right? There's so many things that you can do with an op amp. And the thing is it's all in real time, right? So if I want to integrate on a microcontroller, right? Right. I have to break the signal, digitize it, break it up into these parts, and then, find the area, and sum it to the next area, and then sum it to the next area, and sum it to the next area, and sum and sum and sum. And so microcontrollers can get overloaded. And since a lot of signals are analog to begin with, like sensors and things like that, we live in an analog world, right? A continuous value, continuous time world, right? This can manipulate the signal so that the microcontroller can handle it, right? You should have seen a microcontroller in your programming class, or maybe you've seen it in an Arduino, right? That's what I mean. So it's everything is digital and in discrete time, right? So, and the thing is when you start going in higher and higher frequencies, well, the analog to digital converters that you need to get it into the digital circuit might not be fast enough. And so you have to do things in this space or this design space. But really, it's not one or the other. You use the right tool for the right job, okay? And if all you knew was microcontrollers and EE112, you might never get anything to process, right? And some things are just too difficult. The circuitry is just too complex to do with just op-amps, right? So and they can be somewhat inflexible, right? Kind of once you select your resistors, you're kind of stuck. Although there is a way to program op-amps, but that's a different story, all right? So really, op-amps, really important. You might have seen two configurations that you should be familiar with. And almost everything can kind of be done by combining these two things and manipulating what devices go where. All right. So what I want to do first, I mean, these derivations are out there, right? So nodal analysis is the way to go. I assign my currents and my voltage drops, right? So this is a behavioral source. And so V out equals some gain times the difference of these two inputs. Now this will be an important thing in 110. I know usually we think of it as infinity, but to derive it properly, you kind of have to let it go to infinity. You can't just say it's infinity. So because this is a behavioral voltage source, there's only one unknown here, right? So we have V in, so we have IZ1 equal to IZ2. Okay. And what we do, So we don't know Vx, and because V out depended on Vx, we don't know that either, right? So anyway, V plus here, it's tied to ground. And ground is like a voltage source. It's like a battery with no potential, right? And so its ideal grounds will set whatever it touches to 0 volts. All right. And then here is actually Vx. So V out actually equals minus AV, which will eventually go to infinity, times Vx, right? So now, so again, this isn't what today is like really, I mean, I have to go faster than maybe the first time you've seen this, right? But really, now I set this to infinity, and what happens is Vx goes to 0, okay? So then I can come back here. So if Vx is very close to 0, then V out over V in equals minus Z2 over Z1. All right. So now you kind of have that, right? But I assumed this went to infinity and the op amp is ideal. Rn goes to infinity. The power supplies go to infinity. Everything is, but now we've shown that for that configuration, Vx equals V plus, and in that configuration equals 0. For the non-inverting, Vx equals V plus equals the input voltage, right? So the thing is now if I were to do this, okay. Well, now I know that V out equals ZC divided by ZR times minus 1. All right. From Wednesday's class, we get 1 over SRC, and that's inverted. All right. So this block, right, has what you might have called gain in EE98, but we're going to give it a special thing called the transfer function, and it's just called H, right? Well, now if I have this, right? Well, we might have called it gain in our circuits class, but it's really going to be this, all right? And because op amps isolate things from each other, right? Just making sure I don't. So if I have this circuit, right? Well, I know that this is minus R2 over R1. I can give this a name, you know, V1, this is in V1 and that's V out, right? But this first gain stage is that, right? This second stage, excuse me, is minus, and that's 3, we can call that 1, all right? So I'm just reminding you is that all you have to do is multiply this by this, and now V out over V in, minus times minus is positive, R2, R1, R3, C, 1, S. Okay. Now, if we recall, S, we're going to ultimately, when we want to look at things, are going to turn it into that kind of phasor by saying it's J omega, but S is a lot easier. Also, when we want to use the Laplace transform, we do something different there, all right? But that S is the impedance, right? So we're in the frequency domain, all right? And then if you, and again, today's, I'm not going to derive it, but in differential equations, you should have touched upon the Laplace transform and the inverse Laplace transform, right? And that S, right? So if I take the inverse of that, right, in time, I'm just going to get an integration. It's going to be scaled by R2, R1, R3, C. You know what? That's too sloppy. And actually, it would be 0 to T, and I would have to change this to a dummy variable, right? Now, you can do this in the time domain. But you have to use nodal analysis, right? This would be still V in minus Vx divided by R. But what's that current there, right? Well, the current in a capacitor is what? It's C dV dt, right? But what is the voltage, right? It's actually Vx minus V out. And of course, you would have to, you would remember that Vx was 0 because the op-amp is ideal and all that. So you can, then you have that relationship, and then you just invert it, and then you get the integration from there, okay? So you can do that in the time domain. There is a nonlinear function. Okay. And what happens is, well, if I don't allow things to change very much, I can kind of convert this into a resistance. Really, the diode equation is nonlinear. So again, I would have to do V in minus Vx divided by R1, and the current through that diode forward bias is approximately equal to something called I naught e to the V diode. And you'll find out what all that means in MADI 153 and EE 128. And then that VD would be Vx minus V out. Of course, now we know that that's 0. And ultimately you get V out equal to the negative of a log function. Okay. So these are just kind of hints that hopefully will help you get you started, or at least know where to ask questions when you can email me. Now, yeah, the afternoon, I'm probably going to have to repeat, right? And I'll go over RMS again and the same thing. But you're certainly welcome to come then, right? And I will post this recording somewhere when it's processed. Okay, so I got time for a few questions.
Real quick, Professor.
Yeah.
That dummy variable that you wrote.
Yeah, sorry, yeah. But
Or is it like?
So here's the thing, right? RMS, right? It just turns into a constant, right? No time. But if I have a function of t that's equal to the integration of something, t dt, well, you can't limit and the thing you're integrating in can't have the same thing. So you have to change the variable. I'm calling that tau. So that when I integrate this, I get what the integration of tau is tau squared divided by 2, 0 to t, 1 over RC, right? And then I substitute. Then I get t, there's my function of t squared divided by 2 scaled by 1 over RC. We'll go over that later. That's part of the class. You might have seen it before, right? But yeah. And of course, there's something here that's not that can be forgotten. Since we started at 0, right? F of t equals this, t greater than or equal to 0, and it equals 0, t less than 0. We have a special function for that. We call it ut, which is a step. And before time equals 1, it's 0. After, before equals time 0, it's equal to 0. And after 0, it's equal to 1. And I could just multiply that by that function. But that's the long way of saying it. Anyway, it was so actually, I'm going to leave the meeting because I kind of want to, but so you guys can stay and chat, do whatever, work on things. I just have to go to another, but again, you don't have to stay till 1:30 when I start up again. And if I screw up the link, I'll just send out another link or something.
Professor?
Yes.
We don't have to become again at 1:30, right? The
You
same.
do not have to come. I'm just
Okay.
saying, hey, you're not uninvited.
Okay.
Okay.
Yeah.
All right. Sorry, I really got to scoot. Take
And
care.
for the next
Oh.
meeting, for the next Friday meeting, we have to be in person, face to face.
That's right. Lab starts.
Lab
Yep.
starts. You
Yep.
gonna be there or someone else, Professor?
You know, I'm gonna. Oh no, the TAs will be there. I want to
Okay,
come
okay.
by and say hi.
Sure.
But no, the TAs are the TAs.
Okay. Thank you, Professor. Have a nice day.
All right, you too. Take care, guys.
Don't forget to stop the recording.
Oh yeah, that's probably good. Yeah, we don't want a hot mic. No, I'm just gonna stop it.